Functions of multiple variables is a really natural topic for most students at the Calc 3 level. Usually the difficulty lies in kind of digesting all of the new terminology and finding a way to personalize it and internalize it and sort of make it your own. Here's some examples of the types of functions that you'll commonly encounter in a Calc 3 class. The first type is explicitly defined functions. This is probably our most comfortable launching off place. This is where the height is just straight up a formula that depends on x and y. So I've graphed a basic kind of downward facing paraboloid. The next type is implicitly defined functions. I think that most students are familiar with this equation of a sphere of radius 1. That's an example of an implicitly defined function. And then just like when we were defining curves, it's equivalent to give a parametric definition or to give a vector definition. And I really think this is the most descriptive way of defining a function. I mean, you can either put it inside a vector like this, and then it's like sort of vector defined, or you can just straight up list x and y and z, and there it is, defined parametrically. A cross section of the graph where one variable is constant is called a level curve. For example, in this, let's do the sphere first. In this sphere, if I picked, for example, maybe the curve where z is equal to 1/2, the height of the sphere goes up to 1, so I would get a kind of circle right there. If you want to, you can think of a plane at height 1/2 that has sliced through this sphere. So maybe for this one, I'll pick, say, for example, x is equal to 0, and that would be slicing the graph in this direction, and I would get this parabola right here. And then maybe for this last one, I'll pick, say, for example, z is equal to 2, and let's suppose that that's right here, and I would get like a circle like this. We're a bit back to college algebra, but we're again asked to find the domain of a function, and I've just kind of brainstormed some of the ways that a function could be undefined, and we're trying to exclude those points. So you can't divide by 0. You can't take like the fourth root of -1 or the square root of -1. You can't take the logarithm of a non-positive, so the natural log of 0 or the natural log of -3 is not allowed. And if you're doing sine inverse or cosine inverse, those values that you plug in have to be strictly smaller than 1. So usually these are just sort of basic analysis problems. You just kind of have to look at the function and ask yourself what would make this undefined. Let me do some examples. I'm going to calculate the domain of the natural logarithm of 1 minus x squared minus y squared. So I have to require that the thing inside the logarithm, the argument of the logarithm, is strictly positive. I'm not allowed to take the logarithm of a negative or 0. So I have to require that 1 minus x squared minus y squared is strictly bigger than 0. Just as a quick example, if I had like the square root of 1 minus x squared minus y squared, then this would be greater than or equal to. So be mindful of whether or not you want to include 0, because that affects what kind of inequality symbol you're going to use. So if I just solve this, I get 1 is greater than x squared minus y squared, x squared plus y squared. So this is a circle of radius 1. And what I'm looking for is all of the points for which x squared plus y squared is less than 1. So if I choose large values of x squared plus y squared, then it would not be less than 1. But if I choose small values for x squared plus y squared, it will be less than 1. So the way that we denote, if you have like greater than or equal to, you're going to use a solid line. And if you have strictly greater than, you're going to use a dashed line. I think this is probably consistent with other things that you've studied. So in this problem, I have a strict inequality, so I'm going to make a dashed circle, do my best to draw a circle. And then, as I explained, we are looking for the small values of x and y, so these are the values inside the circle. If you're ever stuck and you don't know, am I trying to include the points inside the circle or inside some region or outside some region? What you can do is always just pick like a test point. So if, for example, I test 0, 0, then, and I plug it into this, I would have 1 is bigger than 0 squared plus 0 squared. And that's true. 1 is bigger than 0. So that means because it's true, I am going to shade the part of the region that contains the test point. If it was false, I would not shade the part of the region that contains the test point. In math, the way that we encode the idea of is close to is by using an interval. In 2D, what we're familiar with is some little segment of the x-axis as being an interval, or maybe a segment of the y-axis. So we need to somehow try to interpret that in 3D. Well, the way that we use the definition in 2D is to imagine that there is some center point of the interval, and then the edge of the interval is some boundary point that you get there by either adding some small distance, I'm going to call it delta for small distance, or maybe subtracting some small distance. So what is there? There's a center, and then we're looking at all the points that are some distance away from the center. So if I'm going to copy and paste that into 3D, what I'm going to need is some kind of circle in the xy plane, and that circle has a center, x naught, y naught, and then there is some radius of the circle, delta. And what we're going to be concerned with is what happens when you look at all of the places on the graph that could come from the points that are inside that little interval that is now a circle. Now I'd like to try to encode the ideas of sort of being inside the region versus on the edge of the region. And here's my observation. If I pick a point on the inside of the region, then no matter how close I get to the edge, I would always be able to find an interval small enough that was centered at that point, and that entire interval that I found is inside the region. Also in 2D, no matter how close you picked to the edge, if you are truly inside the region, then I could always find a circle small enough so that circle is centered at the region, so that that circle is contained in the region. On the other hand, if I pick a point that's on the boundary, like this point right here is on the boundary, then no matter how small an interval I draw, I will always get some points that are outside the region. And likewise over here, if I pick this point there on the boundary, then no matter how small a circle I draw, I am always going to include some points that are not inside the region. So that's the way that we define the interior and the boundary of a region. And both of these, I've tried to draw it so that on the left-hand side, the region does not contain the boundary, and on the right-hand side, the region does contain the boundary. All right, last little bit of terminology. A region is open if all of the points are interior points. So that means that it does not have any boundary points in it at all. This example of the domain of this natural logarithm function that we found over here, it doesn't contain its boundary, right? All of those boundary points are excluded. It only contains interior points. So this domain was open. The idea behind bounded and unbounded, I wrote unbounded here. This is wrong. This is the definition of bounded. So the idea that we're trying to encode is whether or not the region kind of goes on forever. So one thing you can say about regions that don't go on forever is it's possible to draw a circle around them. So this region right here, I can draw a circle around it. This region right here, I can draw a circle around it. So both of these are examples of bounded regions. Regions do have to be, they're either bounded or unbounded. You can either draw a circle around it or you can't, but the definition of open and closed is not all inclusive. It's not like all sets are either open or closed. Both of these regions right here have a portion of the boundary that is not contained in the region. This left-hand endpoint over here and this whole dotted side right there, those are both boundaries of the region, but they're not contained in it. But then they do have some of the boundary is contained in the region. So both of these two sets right here are neither open nor closed. Two more quick examples of open, closed, bounded, unbounded. I've graphed a parabola and I'm looking for all the places that y is greater than x squared. So I want the y's that are above the parabola. So that is all of these points right here. So this region does not contain the boundary. All of the points are interior points. Any one of these shaded points that I picked, I could always draw a circle small enough so that all of the points are in that circle are inside this region. So this first example is open. Also, it just keeps going and going and going and going and going. It never stops going up. So if I draw a circle this big, I have not entirely contained the region because it keeps going, and I've missed some of these points up here. Even if I drew a bigger circle, because it keeps going, I would still miss those points up there. So no matter what, there is no way that I can draw a circle big enough to entirely enclose this region. So this is an unbounded region. All right, so over here, I have graphed an ellipse, and this time I want the x squareds and y squareds to be very small. So like before, I am shading the inside of this ellipse. Okay, now, this ellipse has a boundary. This region has a boundary. The boundary of this region is the ellipse. And all of those boundary points are contained inside the region. There isn't a dotted or dashed line anywhere. So that means this region is closed. Also, it is bounded. It is possible for me to draw a circle. There I did. I have drawn a circle and the entirety of the region is contained inside that circle. So this region is closed and bounded. I've drawn it off the screen. Okay, let's move it over here. All right, so this region is closed and bounded, whether or not you can see it. It is, and I'll just mention that is the gold star for regions. Those are the regions that mathematicians love the most. When you let me assume that regions, especially domains, are closed and bounded, then it's really easy for me to prove things. So be on the lookout for closed and bounded regions. You may have seen images like this before. They're called topographical maps. And the idea is it's a way to take 3D information and represent it in a 2D graph. So the point is that you take a bunch of level curves that are all the same, and you slice them evenly, and then you just graph all of those level curves on a 2D graph. And this is the observation that I'd like you to have about topographical maps. So let's suppose that I sliced this hill in a bunch of evenly spaced ways. Okay, this worked out good. I didn't quite make them level. Let me try again. All right, so now let's draw these circles on our 2D picture. So what I'm going to get is, the first one is obviously going to be a circle. So I'll draw a kind of like sort of circular shape. That's this bottom level here. Maybe we're like z equals 1 or something. So now the next circle that I draw, you can see because the left side of this hill is not very steep, when I go over to the next curve, I go over quite a bit before I get to the next curve. But on the right side, because it's very steep, I don't go over very much before I get to the next curve. So what that means is, in the topographical map, the curves that are close to each other are going to be, that's going to be the steeper side. And then the curves where there's like a bigger gap, that's going to be the less steep side. So what's next? Z equals 3. Still really steep over there, but not as steep on this side. Can you see how because it's not steep over there, I'm like leaving a bigger gap? I feel like that makes sense. So then this is the Z equals 3. And then the last one is just going to be, I try to just kind of make it like just a point right there. So I'll just put kind of a peak at the top of this, maybe just a very small ellipse for Z equals 4. A good way to really understand a surface and how the topographical map should look is to have the computer graph it for you. So what you can do is just take whatever curve or surface that you're looking at, whatever function of multiple variables that you're looking at, and plug it into CalcPlot3D. And then you can add a slider as z equals a constant, and the computer will give you a slider, and you could imagine that level curve moving up and down. I'm getting some circles for the low values of the level curve that are getting bigger and bigger and bigger and bigger and bigger and bigger. And now they're quite big circles. It goes off the page. And then they get bigger and bigger and bigger. And I think that here they're going to be like huge circles, that aren't going to be part of our topographical map. And then here it's going to be like kind of so big that it sort of looks like a straight line. And then as we go up, we're going to see smaller circles coming down the other way. And then that should make, you can see down there are little circles down there. There's the kind of cross-section. Maybe if I move it up a little bit there, now you can really see that there should be circles. In fact, I think it will, it'll even make one for you. Okay, see, look here, it's generating some nice, so this is where the first, it goes down to -1. Let's make it go down to -2. And then, number of contours 11. Can I make it 22, computer? Okay, create plot. What'll it do here? Oh, it's still giving me my little graph. Okay, look at that. Oh, cool. So you can actually even have the computer, if you're ever curious what the topographical map should look like, look at labels each one of these. And as predicted, over here, this is where the circles are that came from the tall values of Z. And then over on the positive X side, those corresponded to the negative values of Z. That was when the slider was down there. So this is like a real convenient, real easy to understand way to communicate three-dimensional information using a two-dimensional graph.